talk about recurrence of planar graph limits.
Yeah, thank you. Thank you. Okay, so first I need to apologize because this is going to be basically a repeat talk of the talk I gave in September in Banff. Now, that talk also started with an apology. So if I want this to be a repeat talk, I have to start with an apology now as well, and I've just done so, so we're on the right track. Okay, so still I think that most of the people in the audience did not hear this talk, so I feel fine, and those who did, they have other things to do, so I'm not concerned. Okay, so the correct title is that Recurrence of Planar Graph Limits, and this is work with Asaf Nachmias, but I'm going to at least mention a couple of other works at the end, so this is more complete title. But I'm just going to mention these other works, and if you really want to hear something about them or the proofs or anything like that, then you will have to come next month to Warwick, and then I will talk about these works. Okay, so let's start with this. Okay, so we have uniformly chosen triangulation or quadrangulation, planar triangulation or quadrangulation on n vertices, and we ask, what does it look like? So here's one example of a quadrangulation, or at least it's almost a quadrangulation because the outer face is not a quadrangle, it has more faces, more edges, but we're not really concerned about this, so let's just imagine that the outer face also have 4 edges.
I think there is a pentagon somewhere.
There's a what?
There is a pentagon somewhere.
Yes, this image is by Nicola Curena. Somehow, I don't know. Is it too small? Can you see this? I'm not sure. So, but I also have an alternative picture which you might recognize. I don't know if you recognize it. I didn't really ask. I didn't really. I didn't really ask Regal for permission. Is he here? No. Okay. He's here. Okay. So is it fine? Yeah, thank you. So this is a triangulation, and again, the outer face is not a triangle, but let's ignore this and imagine that it is. So the question we ask is, what does it look like when n is very big? And one standard way to answer this question is to scale the distances so that the object that we have of roughly of a fixed size. So this means that we need to scale by a factor of n to the minus quarter, and then the diameter is roughly 1. I mean, it's tight. And then there is a limit, and this limit is called the Barnian map, and this is a picture of the limit. Somehow it's kind of hard to see what's going on. This is a 3-dimensional object, okay, not 2-dimensional. There is the other side. So this is not what we're going to talk about. We're going to talk about what happens when you don't scale the distances at all, and then you get a bigger and bigger object, but you only look at the object locally. You only want to know what happened in some finite radius around a fixed vertex. Okay, so let's make this more rigorous. So suppose that you have a sequence of rooted graph with specific roots, then you say that you have a limit if for any finite radii, any finite radius that you pick, you see a limit. You see that the sequence of the ball of this radius around the root converges to something, and this is a discrete space, so converges just means that it looks the same from some n0, from big N, and on. Okay, so this is a fixed sequence, a sequence of graph and fixed root. So let's say that you just have graph and with no root, then you just choose the root randomly, uniformly at random among all vertices, and then you have some distribution on, for every fixed r, you have some distribution on what the ball of radius r around the root looks like, and if this distribution converges, then you say that this object, so this will be a random infinite graph. I mean, for any reasonable sequence of graphs, this will be infinite. So you have a random infinite graph with a specific root, and we say that this is the distributional limit, or the Benjamini-Schramm limit of the sequence of graphs. So here are a couple of examples. Simple example: if you have a path of length n, then what you see at the limit is a copy of z, because the root is not going to be one of the endpoints of the path, or it's not going to be a neighbor of the endpoints, etc. If you have Erdős-Rényi random graph with some with probability of C over n of every edge existing, then at the limit you get a Galton-Watson tree. Notice that in this case we have two randomization. I mean, the sequence here is also random, okay, and also we choose the root to be a random root. But then it doesn't really matter that we chose the root to be a random vertex of the graph, right? We could have chosen any fixed vertex because the graph itself is not just random. The distribution is invariant under some transitive group, right? So it doesn't really matter which vertex we choose. If we choose it before we choose which edges are present and which are not. Okay, a more interesting example is what happens if we have a binary tree, finite binary tree. Then a natural guess might be that you get an infinite binary tree, but that's not what you get. What you get instead is called the canopy tree, which is an infinite binary tree, but from the point of view of the leaves. Okay, because when you have a binary tree, then with probability roughly half you choose one of the leaves, and probability roughly 1/4 you choose a neighbor of the leaves, etc. So basically the probability that you choose the root or anything that is even at least at some fixed distance from the leaf goes to 0. Okay, so you are going to choose one of the leaves or the neighbors of the leaf, etc. So that is what you look like, and of course you need to root it somewhere. So the root will be a leaf with probability half, and this with probability 1/4, 1/8, etc. Okay, so let's go back to the uniformly chosen random triangulation. Suppose that we do this for the random triangulation. What do we get for the distributional limit? So apparently we do get something. There is a limit, and this was a result of Angel and Schramm. And this limit is what we call the uniform infinite planar triangulation. Okay, and really, I'm not going to say anything specific about the UIPT or UIPQ or other models, because a lot of them will have the property that I want, which I'll mention in a second. And in any case, for many models, we expect to have some universality and to have converge in some sense to have similar distributional limits. Okay, so here's a picture by Nicola showing some small part of the UIPQ, I guess, and also slightly bigger part, because you can actually see all the vertices in this direction from the point of view of the root. Let's say that this is the root. Okay, so what do we know about the UIPT and similar models? So here are some some properties. It's one-ended, meaning if I take out finitely many vertices, then I get only one infinite connected component. You know that the critical percolation threshold is half, just like in Z2. We know that it has the Liouville property, meaning that we don't have any bounded non-constant harmonic function. This is also the same as Z2. But in other ways, it's very different, and the trivial difference is that the degrees are unbounded. I mean, we have some vertices that have a high degree. As trivial as it is, this is basically what this talk is about. We'll see this in a second. And the growth rate, the volume growth is r to the fourth instead of r squared. And we also know that it's subdiffusive, meaning that the heat kernel decays more quickly than in Z2. Well, okay, more slowly, actually. And the question we address here is whether this graph is a recurrent graph or a transient graph, meaning if we start a simple random walk on this graph, does it return to the origin finitely many times or infinitely many times, almost surely. So, Z2, of course, is recurrent. So it was a conjecture that indeed also the UIPT, UIPQ, and similar model also should be almost surely recurrent. But why would you conjecture? Why would you conjecture this? So let's talk about what would have happened had the UIPT had bounded degrees instead of unbounded degrees. So we have a theorem of Benjamini Schramm that if you have a sequence of a finite planar graph with bounded degrees, then the limit is almost surely recurrent. So, for example, all the examples that we had before, we had Z and Galton-Watson tree, and not the Galton-Watson tree because it's not the planar. Sorry. But more importantly, let's say the canopy tree that we had, the infinite binary tree, which is not the limit, is transient, but the canopy tree, which is like the same, but from the point of view of the leaf, it is recurrent because there's only one way of going to infinity, and this is just a path. Okay, so it has to be recurrent. Okay, here, yeah, the example I just mentioned, and bounded degree is really strictly necessary. So here's an example of why it is necessary. So suppose that we had the canopy tree, but instead of just one edge here, we would put 2 edges here, and 4 edges here, and 8 here, and 16 here, etc. So we can do this for the finite graph, and the limit. Now I'm slightly cheating here, but I won't mention why I'm cheating. You have to consider a sequence that goes a little bit more slowly than 2 to the n. But let's just pretend that it works also with 2 to the n. Then, if you get this as the limit, then this is actually transient, because again, if we look at the location of the random walk only on this path, the only path to infinity, then it has a bias. It goes with probability 2 to the third, 2/3 it goes this way, and only 1/3 goes this way. Of course, it might go into this part, but this is just a finite graph. So it goes here, come back, and when it's on this path, it has a bias. So this is a transient graph. So we actually do need a bounded degree. That's important. Okay, so our main result is an extension of the Benjamini-Schramm theorem. It says that instead of bounded degree, we might get by with exponential tail for the degree of the root, meaning the probability to decay exponentially. Okay. It was already known by some bijection or some other way that the degrees of the UIPT and UIPQ has exponential tail, and since then we had a few more examples. I think that they were even mentioned in earlier talk. Okay, and just for sharpness, it seems like exponential is really rather a strong requirement. One might wonder whether maybe it is enough to just have expected degree to be finite, or maybe a finite variance or something like that. So this is not enough. Even slightly farther tailed than exponential, meaning even something that decays stretch exponentially, like e to the minus n to the alpha and alpha less than 1, even this is not enough to force the limit to be recurrent, and basically the counterexample is very similar to the canopy tree that I had. You just put different weights and you can put them so that it's almost exponentially decaying, but still it's going to be transient. Okay, so these are the results. Any question about the result? No, good. Okay, so let's talk about circle packing and how it relates to this result. How do we use this? So we have some finite simple planar graph, and we want to find some nice representation. There are many ways that we can draw it in the plane, so we want to find one that is somewhat canonical. Okay. So one such way is the circle packing theorem, which says that if you have a finite simple planar graph, then you can draw the graph as a tangency graph of a circle packing, meaning for every vertex we have a circle, and two circles are adjacent in the graph if and only if the two circles are tangent in our drawing. So it looks something like this. This vertex is this circle, this one is this one, etc. Okay, this one is this one. Right. So in what? Okay, so maybe this is a nice drawing and all the edges are now a straight line, but in what way is this canonical way to draw? Well, it's not. In this case, it's not, because, for example, we might take this vertex, which goes to this circle, and then we can just move it a little bit over here and over here and adjust the radii. It's not a problem. But notice that it's somewhat harder to do this with this circle because it's adjacent to 4 other circles. If we move this one, we need to modify one of the other circles. Okay, and if it would be completely surrounded, then we wouldn't be able to move it at all. So basically, what happens if the graph was a triangulation to begin with, then we don't have any degrees of freedom except Möbius transformation. So Möbius transformation always preserve tangency and preserve the circle, etc. So these we are stuck with. Okay, so how is this circle packing stuff useful for us? So here's the theorem of Hehn Schramm on 95. If we have a graph and we look at its circle packing, and now we have an infinite graph, infinite planar graph, and suppose that its circle packing actually cover the entire plane. So what do I mean by cover? Maybe I should draw this. If we have 3 circles here, then I say that they cover all of this, but also they cover this part. Okay, so we include this in what the circle packing covers. So when I say that it doesn't cover infinite, I have an infinite graph, I might have a graph that looks, I don't know, like this, and then here there are simply no circles. Okay, that might be the case, and then it doesn't cover everything. And it might be the case that that the entire graph, although it is infinite, the circle becomes smaller and smaller. So we actually reach some boundary here. Okay, and the entire circle packing is contained in some finite domain. Okay, so if this doesn't happen, if it covers, actually does cover everything, then the graph has to be recurrent. And again, bounded degree is important here because, for example, you can look at this circle packing. So this is a circle packing of the standard triangular lattice. So this is recurrent, okay? But you can just add some circles to make it transient. Okay, so if you add a circle here and here, and then here a circle and another one, and these two, and here you can see this, but well, I can't see this either. But let's say that you add even more circles, you can just make, you know, the degrees here very big. So a random walk that got to one of these will have a bias toward the right, and also the probability for it to leave this infinite path will become smaller and smaller. So there is a positive probability that it will just go away. So this graph is tangent. So bounded degree is really necessary here. Okay, so I haven't yet said anything about how this is useful for the distributional limit, but let's talk about why this theorem is true. Okay, before seeing how we use it. So this is I don't know how to say this. This is more or less equivalent to the proof, but in different words, and also produces a quantitative version that we need. Okay, so let's say that we have a bounded degree triangulation. So first thing that we need to know, and very important, that it's called the ring lemma. It says that we cannot have, you know, if this radius is say 1, we cannot have that one of these is going to be, you know, very small circle. Okay? And this is just because it is triangulation. So let's convince us of that before we go on. So the proof is basically that if this is a circle and it has a neighbor, let's say it has only, I don't know, 7 neighbors, and this is a very small circle, then this very small circle cannot have 2 very large neighbors. By neighbors, I mean the circles that are tangent both to it and the original one. Okay, because if these two would be, say, 100 times the size of this one, then they would just overlap. Okay, so one of them has to be only, as I said, less than 100 times the small circle, and then you look at the 2 next circles. So let's say this is the smaller one. So we look at the circle over here and the circle over here, and again, they cannot both be, you know, much bigger than the circle that we had before. So each iteration can only produce something that is bounded by constant time the previous radii. So if we started with something very small, we cannot possibly go around the central circle. And of course, if the entire graph is a triangulation, so the neighbor cannot be much smaller than this one, but if this is also surrounded by circles, then of course it cannot be much bigger than this one either. So the ratio is bounded from both directions. Okay. So how do we use this? We use this to prove the following lemma. So here I'm going to assume that you are familiar with the electrical network theory of random walk. We said that basically we look at the graph as an electric network, and each edge is a unit resistor, and then we calculate the effective resistance and see whether it, what we get. And we know that a graph is recurrent exactly when the effective resistance from some vertex to infinity is infinite. So here I'm going to have a lower bound for the effective resistance across an annulus. So let's see the picture. We have a big circle packing with lots of circles, and then we have an annulus. The inside is the blue circle here, and the outside here is the red. And we ask what is the effective resistance between the set of vertices here inside and the set of vertices here outside, and we claim that this is at least some constant that depends only on the well, basically on the ratio between these two radii, and also on the maximal degree of the circle packing. So let's prove this, because as I said, if you know the theory, then this is very easy, and also very illuminating as to the relation between the circle packing and the random walk. So let's see. In order to bound the energy, we need to look at all the possible functions on the vertices of the graph that have value 0 on one side, on the set of, in this case, on the set inside the annulus, and have value 1 on the outside of the annulus, and calculate the energy of all these functions. And then if we take the infimum of all these energy, we take 1 over it, or the supremum of 1 over all these energies, then this is the effective resistance. Okay, just accept that. If you're not familiar with this, just accept this fact. So in order to get a lower bound, all we need to do is find just one function that will give us some number, and this will be a lower bound for the effective resistance. So what is the function that we're going to take? We just take a function that is 0 inside and 1 outside, and interpolate linearly. And by linearly here I mean linearly in Euclidean space. Okay, the function is on the plane, and the function, the value of the function on a vertex is just the value of the function in the center of the vertex. Okay, so if the radius of the of this annulus is r, let's say the inner radius is r and the outer is 2r, okay, then this function goes from 0 to 1 in the distance of r, so this means that the function is 1 over r Lipschitz. So now we can calculate what is the contribution of a single edge to the energy. So what is it? It's at most the distance between the two centers of the circle. So let's write here. Okay, we have this. We have this. This is one center. Call it x. This is y. And of course, the difference between the values of the function at x and at y is at most 1 over r times the distance, the Euclidean distance between them. Okay, so we get that fx minus fy here squared is at most the distance between them over r squared, and the distance between them is up to a constant is the same as the area of one of these circles. Both areas of both circles are roughly the same, right? Because of the ring lemma we just had, the radii are comparable. And we divide by r squared, which is roughly the area of the annulus. But then it means that when we sum over all circles, and circles have bounded degrees, so we use the same circle only boundedly many times. So when we sum over all of this, the sum is just bounded. Okay? And by bounded, I mean it doesn't depend on the circle packing. It depends only on the maximal degree, basically. So if this sum is bounded, means that the energy is bounded, means 1 over the energy is bounded from below, so the effective resistance is at least some fixed number. Okay, and now we can use this and some other known properties of effective resistance to get a quantitative version of how the resistance grows when we take larger and larger balls around a fixed vertex. And what we get is that the resistance grows logarithmically in R, meaning just that if we have a vertex here, we can draw logarithmically many annuli, okay, of let's say of fixed proportion from this vertex to the outside of a circle of radius r. Okay, so each of these contribute at least some fixed resistance. So together we have logarithmic resistance. Okay, and this also, of course, implies that the graph is recurrent. Okay, so that's nice. So this proves the Hersh-Ram theorem. How do we use it to prove the Benjamini-Schramm theorem? Let's recall what it was. It said that if we have a distributional limit of finite planar graph, then the limit is almost surely recurrent. So the idea is that we are going to build a circle packing of the limit, and the circle packing is going to cover the entire plane, except possibly for one point. We will see this in a second. So this is really just a sketch. You take the graph, the finite planar graph. You take a circle packing of each of these graphs, and then you choose a random vertex. Okay? This is how you construct the distributional limit. Okay, but then you use this vertex in order to change the circle packing. You center the circle packing around this vertex, and you scale it so that this vertex, the circle of this vertex, is of size 1. Okay, so you get basically all the time you get a circle of size 1 and some changing distribution of circles around it, of a circle packing around it. So so the idea is that these circle packing, they actually live in a compact space, right? Because you know exactly how many neighbors this circle has, and each of them cannot be too small or too big. So we have some subsequence such that the circles around the root converge, okay, or more precisely, the distribution of the location of the circle converges, and the distribution, and this is true for any finite radius. So basically, you get a distribution on infinite circle packing, and somehow the main point here is that you have to prove, and this I'm not going to say how to do this. You have to prove that this circle packing covers the entire plane, and this is what they proved. It might have one accumulation point, but this is the most it can have. It cannot be in a bounded domain. So the limit has actually to be recurrent almost surely, and this one accumulation point that you might have, we can always take care of it, because we can always just look at what happened outside the radii of say 1, okay, away from the accumulation point. So basically, you know that this graph is recurrent, and also look at what happens inside this and take an inversion, and then again you get an infinite circle packing which covers the entire plane. So again, it's recurrent, and they have only finite intersection. So together it's still recurrent. So really, the meat of the proof is in this lemma, which is sometimes called the magical lemma. And I'm not really going to say anything about that. Okay, so this has all been with bounded degree. How do we take care of the unbounded degrees? How do we use the exponential decay? Okay, what we do is very simple. We take every vertex. You should think of it as a vertex of high degree, but we actually do this for all the vertices of the graph that we have, and we replace it with the binary tree. How do we do that? So suppose this is the graph that we have. First, we add vertices on every edge. This is just to separate the vertices. So the ball of radii 1 around each original vertex, they are now disjoint. I mean, edge disjoint. And then, if this is one such ball, then we just replace this star. We replace it by a balanced binary tree, and we don't really care how to put this tree, as long as it's roughly balanced and planar. Okay, we don't do crazy things like connect this to this and this to this. Okay. So we call this the star tree transformation. So what happens when we do that? Well, what happens is that we get a new graph, and how is the new graph? I mean, how is recurrency of the old graph related to the recurrency of the new graph. Well, if we look at resistances, we see that this transformation might cause resistances to grow. Not might, it always causes the resistances to grow. So it might be that this graph is transient, but after doing this transformation, it becomes recurrent because resistance are bigger. Okay, so that, for example, if you consider, let's say, this vertex and this vertex, the resistance here between them is 2. It's just a path of length 2. But the resistance here is just, again, the length of the path, and its length is 6, right? So it will threefold. And this is not even the worst case, because if you consider, let's say, these 3 vertices, the one on the left, and these 4, the one on the right, then the resistance between these 2 sets of vertices is actually quite small. It's 1/3 plus 1/4 here. But the resistance between this set and this set here, this is, it's at least 2, because you have a bridge here, that 2 bridges actually that separate them. Okay. So the important thing here is that we control the increase of resistance. In fact, the resistance can grow only by a factor that is equal to the original degree of the vertex. Okay, so to be more precise, you have this lemma. So suppose that we do this star-tree transformation, but the new edges are not going to have resistances of 1 like before. They're going to put some weights on them. So we're going to make them of smaller distance. The new resistance is going to be 1 over the original degree. So this is the same as, from a random walk point of view, this is the same as putting a weight of the original degree on each of these edges and doing a weighted random walk, meaning if you choose the next neighbor, proportionally to the weight of the edge. So we claim that that if we do that, the new graph is actually equivalent in the sense of the resistances stays roughly the same up to some constant. They stay the same in the old and in the new graph. So this means that if we look at this graph, the graph equipped with these resistances, and prove that this is recurrent, then it implies that the original graph was recurrent. And this is exactly what we do. Okay, so again, how do we do that? So here comes the exponential decay. If we have an exponential decay, in some sense, which I'm not again going to say precisely what it is, the degrees of the vertices in the graph, they grow logarithmically. Now, it's again, I didn't write exactly what practically logarithmic means, but one sense one thing that it means that the probability of a simple random walk as it walks along the graph to encounter a vertex whose degree is more than logarithmic in the number of steps that you do. Okay, the probability decays to 0, and it decays really fast if you put even a constant. If you put a large constant time log of the number of steps that you do, you're not going to encounter a vertex of this degree after a while, of course. So this is we have basically two logarithmic two competing logarithmic factors, if you will. Okay, one is what we got from the electrical resistance lemma. If we look at the electrical resistance between a vertex and a ball of the outside of a ball of radius r, then the resistance is logarithmic in r. And on the other hand, we know that we put low resistances on the edges, but we don't encounter vertices of degrees higher than logarithmic. So these two factors actually cancel each other, and then it means that you get a lower bound for the resistance between a vertex and the outside of a ball, which is at least a constant. Now, this is not very exciting because, of course, it is at least a constant, But the thing is, you can do this, for any finite subset of the vertices. You don't have to start with just one vertex. So if you take a ball of radius 100 and do the same calculation from the resistance from it to the outside of a ball of radius r, then you still have logarithmic increase of the resistance. You still have logarithmically small resistances that you put on the edges, and they still cancel, so you still get a lower bound of some constant. So this means that the resistance from any finite set to infinity is at least a constant, which can only happen if it's actually infinite. If it's finite, then if you take a large enough set, then the resistance from the outside to infinity has to be small. We can do this. I didn't write it, but we can do this quantitatively, and then I'm not sure exactly what we would get, but probably the resistance would go something like log, okay, instead of just logarithmically. But the important thing for us is that we get that the graph is recurrent. Okay, so this is not the end. As I said, I promised to deliver some other results that are related but not quite related. So before going that way, I just want to mention an important open problem in the context, in the specific context of the UIPT, UIPQ, etc., which is, if you look at the UIPT or UIPQ, or maybe if you look at one of them after doing this star-tree transformation because you want to have bounded degrees, we can ask ourselves, and it turns out to be important, we can ask ourselves whether we have big circles. And by big, I mean that they have to be macroscopic in the scale that we see them. So do we have a circle at distance r from the origin whose radius is at least some, I don't know, r over 100, okay? Or even r over log r, something like that, okay? Or do we have only small circles, let's say circles that are of size r to the alpha, and alpha is less than 1. So this is still open, and it would be very useful to know, because then we would also get all kind of probably hit kernel estimate and return probability estimate. These macroscopic circles are very annoying when trying to do that. Okay, so let's talk about these other things. I still have 15 minutes, probably too much. So let's remember what we have in the Hershram theorem. Okay, so I mentioned it, but again, the graph is one-ended. If we take out finitely many vertices, we are left with only one infinite component. So in the case of planar graph and circle packing, then it just means that the carrier, so the carrier is just the union of all the circles and these small triangles that between them is simply connected. Okay, so a more complete version of the Hershram theorem would be that if we have a bounded degree one-ended triangulation and circle packing, then the circle packing covers the entire plane exactly when it is recurrent. Okay, we only prove one side of this. We prove that if it covers the entire plane, then it is recurrent. And in the other case, in the transient case, then we actually have a circle packing that covers some finite domain, and we can also choose this finite domain basically freely. We can take a simply connected domain, and we would have a circle packing that covers exactly this domain. So here's one example of hyperbolic tessellation, and here's another. And this time packed inside the square instead of a unit disk, and we can have this again with any nice enough shape, not nice enough, and with any domain, open domain basically. I think that also this is also an open problem of actually how to calculate this circle packing for general domain in some sense, but I'm not entirely sure this is not something I've been doing. So it seems interesting to me to try to find out how to do this in a general domain. Okay, so let's talk about harmonic function. Function is harmonic if the value of the function is just the average among its neighbors, which is the same thing as if you have a simple random walk, then the value of the function is a martingale. So on one hand, if you have a recurrent graph and you have a bounded harmonic function, then since h of xn is a martingale, you return to the origin with probability 1 and the function is bounded, then the function just has to be constant, right? Because the martingale will converge, and it will converge to the value of the function at any given vertex. But the converse is not true. So for example, zd for any d is also Liouville, even though they are transient. And this is just, for those who are not familiar with this, then this is a good example to consider. If you have a binary tree, you can ask yourself, what is the probability when you start, for a given vertex, when you start at that vertex, what is the probability that the random walk from this vertex gets absorbed in the, let's say, left side, the right side of the tree. Okay, so this probability is, strictly between 0 and 1. It gets, bigger and bigger when you go inside the right side, and gets smaller when you go to the left side. But the thing is that it is a harmonic function. It is bounded and it is not constant. So this function, in a sense, describes one aspect of what the random walk does at infinity. Like it goes this way or it goes that way. And then we can consider other subtrees and ask, does it get absorbed in this subtree and this subtree? What's going on at infinity with the random walk? And this is a general thing. The bounded harmonic function somehow correspond to event or to function, to invariant function. So invariant here means the function now is not a function of the vertices, but rather a function of the entire random walk, the entire sequence of the walk. But we require the function to be in shift invariant. If you shift everything to the left, we want to have the same value of the function. And there is a correspondence between bounded invariant function and bounded harmonic function. It's not too hard to see. So in a sense, this bounded function describes what happens at infinity. Now, again, Benjamin and Schramm, they proved that if you have a bounded degree transient triangulation, then it's also not Liouville. And the proof is not hard. At least now it's not hard. We just take a circle packing, let's say inside the unit disk, and let's say that we identify V and the location of V in this circle packing. Okay, then the location converges to a point, and the point is on the boundary of the circle packing, the boundary of the unit disk. And not just this, it's not always converges to the same point. Okay, and more generally, it's completely non-atomic. So there is no point on the boundary such that the walk converges almost surely there or with positive probability there. So this means that we can take two different parts of the boundary here, the geometric boundary, and ask what is the probability that the random walk converges to this part or the other part. We have an interval on the boundary, and we just look at the function to describe the probability when you start at the vertex x that the random walk will converge into this interval, and this is going to be a non-constant and bounded harmonic function. Okay, and the question is, are these the only harmonic functions? So in a sense, in a geometric sense, we're asking whether the space of all harmonic function correspond to the space of all bounded measurable function on the unit disk. Okay, all the function of this type, but instead of just asking whether the limit belongs to some interval, we just look at the expectation of some function of the limit of where the walk goes to. And our answer is that indeed this is the case. So if we have a bounded harmonic function, then for this function we have a measurable bounded function on the geometric boundary on the unit circle, such that our original function h is the expected value of g of the limit. Okay, so as I write here, it means that there is no more information to find out about where the random walk goes to. Okay, so we might know, for example, we might know that the random walk goes from circle to circle and converges to this point on the boundary, and there is no meaning to saying that it converges from the left or from the right or something like that. Okay, this doesn't happen. If we know that it converges to a specific point, then we know everything that there is to know about it. And just a simple example to see why it's not always the case, but this is really a silly example in some sense. So suppose that we would have a circle packing, but not in the unit disk, but instead in a different domain. So the domain would be, let's say, the unit disk, but minus a slit, something like that. So we have circles here, here, and then here we have smaller and smaller circle that goes to over here. Then if we have a point here and we know that the random walk converges to here, we can still ask whether it converges to here, to this point here, from above or from below. Okay, there is still an event that is not does not have probability 0 or 1, even after the conditioning. Okay, so this is one result, and as I said, if you want to hear about it, you have to come to Warwick next month. The other one is again an extension of work of the Schramm. So we talked about one-ended, and now we want to ask ourselves what happens if we have many-ended graph, more than one end. So here's the result. Suppose that we have a bounded degree triangulation like before, and we have a circle packing. Okay, then we know that the graph is recurrent exactly when the boundary of the carrier, so the boundary of the domain where we packed it, is a polar set. So a polar set means just a set where the Brownian motion hit it with probability 0. Okay. So in particular, even if you don't care about Brownian motion at all, you get the result that in order to find out whether a circle packing of a graph is transient or recurrent, we just need to know what the boundary is. Okay, if you have two different circle packing but with the same boundary, they also have the same recurrent or transient. And in particular, the Hershram theorem, we talked about covering everything or covering just the unit disk. This is just a special case of this, where the carrier, the boundary of the carrier is nothing, meaning it covers everything, or inside the unit disk, then the boundary is just a curve. And that's it, and this is the end.
Thank you very much for the talk and for advertising the board equipment.
Are
there any questions?
Anyone who had a question asked it in band, so I guess.
You mentioned that result about the circle packing having just one accumulation point.
Yes,
Does
the
this
magic
imply there
dilemma.
is only one end? The graph is one-ended?
So the result about having just one accumulation point was about a sequence of finite graphs. You have a sequence of finite graph, and you look at at the limit behavior, and in the limit you get only one accumulation point at the most when you do this in the plane. Okay, so if you consider this on the sphere, you can actually have two accumulation points, right? One of them would be at the North Pole, and one of them will correspond to some point in the plane. So it means that in the limit the graph might be two-ended. Okay, but it's not. Okay, but not more than this. Okay. Yeah, I don't know if that how that answers your question.
Are there any other questions or remarks? If not, then let's thank Ori again.